Alright, welcome back to Thermochemistry Chapter 5. This is Part 3. Okay, we're just going to finish up with Hess's Law. This is a pretty short video, but it's a pretty important concept. And Hess's Law just states that if a reaction is carried out in a series of steps, the delta H, the change in enthalpy for the overall reaction, is just equal to the sum of the enthalpy changes for these individual steps. Okay, so if we look at the example on the right, here we have methane gas, which is being combusted. It's reacting with oxygen to produce carbon dioxide and 2 molecules of water as a liquid. Okay, the delta H for this overall reaction is minus 890 kilojoules. However, basically based on Hess's law, this reaction proceeds in 2 steps. It first takes the methane gas, reacts with oxygen gas to produce carbon dioxide gas and water as a gas, okay, which is minus 802 kilojoules for the change in enthalpy. Okay. Then it converts the water as a gas to water as a liquid, and that takes minus 88 kilojoules. Okay, so if we add those two together, which is shown here, okay, we see that the total delta H for the reaction is minus 890 kilojoules. Okay, and so we can get that in that equation. I'm missing a J here, just to let you know. All right, so if we look at this a little closer in a different example, here we have propane gas, which is going to be combusted reacting with oxygen gas to produce carbon dioxide gas and water as a liquid. So we can actually imagine this step as occurring in 3 steps. Okay, the first is just decomposing to the elements. Okay, so the propane decomposes to graphite and hydrogen gas. Okay, that is a delta H of 103.85 kilojoules. The next step is the formation of 3 molecules of carbon dioxide gas. Okay, and so from there, we basically take our graphite and our oxygen gas along with the carbon dioxide, and we end up forming our 3 molecules of carbon dioxide gas, which reacts with the hydrogen gas and oxygen in the gas, and that is another delta H. Same thing with the third step, where we have formation of 4 molecules of water of a liquid that has its own enthalpy change, delta H3, which is minus 1143. Okay, and if we take and add these 3 together, what we find is we get this overall reaction, which has a delta H naught, or delta H of the reaction is minus 2,220 kilojoules. Okay, so you just add everything up. That's basically what it comes down to when you use Hess's law and you have separate equations or separate steps in a reaction. So at this point, I just want to take a minute and talk about some definitions just to clarify some stuff. So first, we have the enthalpy of formation. Okay, we have enthalpies of the different types of reactions, so enthalpy of combustion and so forth. Okay, and so we abbreviate this as just delta H with a little f, enthalpy of formation. Okay, it's defined as the enthalpy change for the reaction in which a compound is made from its constituent elements in their elemental forms. Okay, well, the magnitude of any enthalpy change really depends on temperature, pressure, and enthalpies of different reactions. Okay, and so in order for us to really be able to compare enthalpies of one reaction to enthalpies of another reaction, we use a set of conditions called the standard state, okay, which is 1 atmosphere and 298 Kelvin, and so we can call that delta H naught, which is just the standard enthalpy change of a reaction. Okay, it's more of like a constant. So the enthalpy change when all reactants and products are in their standard states. Okay, it's just a nice, easy way to compare different reactions. So delta H is well known for many reactions. Basically, it's been measured over time, and so it's actually convenient to go ahead and measure the delta H for all these different reactions which we're interested. And so when we actually come across a new reaction that we want to calculate what the enthalpy change is, we can actually use these published delta H values in order to calculate that. Okay, like we just did, or alternatively, there are the standard enthalpy of formations of a compound, so delta H naught F, which is just basically the change in enthalpy for the reaction that forms 1 mole of the compound from its elements with all substances in their standard states. Okay, we can use these standard enthalpy of formation value in order to calculate what the overall delta H for the reaction is. So what do these look like? So here are the standard enthalpies of formation, so delta H naught F. Okay, this is under standard states, 298 Kelvin in 1 atmosphere. And you can see that basically you can look at something like glucose, and you see that it has a delta H naught a formation of about negative 1,273 kilojoules per mole. All right, you don't need to memorize this chart. It would be given to you. What you need to notice though is that the values that are given in this table are for only 1 mole of product, right? So this is 1 mole of glucose, right? 1 mole of glucose has delta H naught, a formation of about minus 1,273 kilojoules per mole. Okay, so the enthalpy of formation for the 1 mole, but if it was 2 moles of glucose, we take 2 times minus 1,273. And so for 2 moles of glucose, it's minus 2,546 kilojoules per mole. The other thing that you need to note is that delta H of formation for the most stable form of any element is going to be 0. So when we're talking about just carbon, hydrogen gas, or oxygen gas, it's going to be 0. Okay, so you should always remember that. Lastly is that we can use these values in order to actually calculate the overall delta H of the reaction by using Hess's law. And we can use it in this way. Basically, the enthalpy of the reaction is equal to the sum of the enthalpies, okay, of formation of the products. So we take the delta H naught F of the product, so of glucose, maybe we have 2 moles of glucose, so we put 2 in for the N, which is the stoichiometric coefficient, times that minus 1,273 kilojoules per mole, okay, and then we'd add that to the other product, however many coefficients is in front of that, times its delta H of formation. We add those together, and we subtract that from the sum of the enthalpies of formation of the reactants. So same thing here, okay? So once again, we just calculate that, and that's going to give us our total delta H of the reaction. There's a good example in the worksheet and in the homework, so make sure you practice those. Make sure you watch those practice videos in order to understand how to apply these concepts. Okay, that concludes Chapter 5. Chapter 5 is a very tough chapter most of the time. Students have trouble grasping some of the information and getting down most of those calculations. So make sure you spend the time to do so. Good luck.